Hello, we shall now continue our discussion on integration. So, last time we considered trapezoidal rule. What was trapezoidal rule? It assumed that the function varies linearly between every two adjacent points. So, look at this particular set of points. I have a function which is defined at several points. So, between f x I and f x I plus 1, I assume that is a constant. Similarly, between f x I plus 1 and f x I plus 2, there will be another line. So, I assume that to be constant, that I assume that to be linear between every 2 points. Once it is linear between 2 points, my integral is nothing but between every trapezoid, the area is f x I plus 1 plus f x I divided by 2. Between every 2 points, it is half of the it is average of the 2 points multiplied by h. So, between first point and the last point, so the final answer is h into f x naught by 2, h into f x n by 2, and all the intermediate points you have to multiply by h, because both from the left side and the right side half contribution will come. Therefore, each of this is multiplied by h. It is very easy to program this. So, I will leave that as an exercise. Next, what we want to consider is what is the Simpson's rule. Simpson's rule, what it does, it fits a quadratic function between 3 adjacent points. Suppose I have point 2i, 2i plus 1, 2i plus 2. There are these 3 points. These 3 points I will fit through a quadratic polynomial p2ix. What is p2i? This is a Newton's forward interpolating polynomial, which we have already considered. So, I give here the entire expression for p2i. The expression for p2i is f x 2i plus delta 1 f x 2i by h into x minus x 2i plus delta 2 f x I divided by 2 h square into x minus x 2i into x minus x 2i plus 1. So, this is my quadratic polynomial between x 2i and x 2i plus 2, and that polynomial I integrate. So, when I integrate, these are all the steps. Let me define what is my first order difference is f x I plus 1 minus f x I. Second order difference is first order difference at x I plus 1 minus the first order difference at f x I. When you expand everything, it is f x I plus 2 minus 2 f x I plus 1 minus f x I. This is my second order difference, this is my first order difference. So, you put all those differences here and integrate. So, when you integrate, my final result is h by 3 f x 2i plus 4 times f x 2i plus 1 plus f x 2i plus 2. So, that is the end points x 2i and x 2i plus 2 contribute only 1 times, whereas the middle point x 2i plus 1 contributes 4 times, and whole thing you multiply by h by 3. This is called Simpson's 1/3 rule. So, between every interval, this is my integration. So, now let us see that I split the function into many intervals. So, let my function be x 0 to x 2 is one interval. Why is it x 0 to x 2? x 0, x 1, x 2. I need 3 points to have a quadratic function fitting there. Okay. First 3 points, one function. Between x 2 and x 4, that is x 2, x 3, x 4, another quadratic polynomial. Between x n minus 2 to x n, another quadratic polynomial. Okay. So, I have these quadratic polynomial between every 3 points, and so I want to integrate between every 3 points. So, since I started with 3 points 1, 2, 3, then 2, 3, 4, this is the next point. So, you will see that you need an odd number of points, to do the Simpson's rule. Okay. So, between 1 and 3, I will have f x 0, 4 x 1. Between 3 and 5, I have f x 2, 4 f x 3 and 2 f x 4. So, it varies like this. The first point contributes only weight of 1, the last point also has a weight of 1, and the intermediate points will have 4 and 2. Okay. So, first point, 0th point, I have called weight of 1. Next point, this is weight of 4, third point weight of 2, and I go on doing that and multiply by h by 3. This is my Simpson's 1/3 1/3 rule. So, the way I do it would be, I will execute the program and show you how to do that. So, the only problem will come, suppose n is even. If n is even, you cannot implement this, because there will be last 2 points which will create trouble. So, what we do, if n is even, between n minus 1 and n, I use a trapezoidal rule, and between 1 and n minus 1, again this is an odd number of points, I shall use Simpson's rule. So, whenever n is odd, Simpson's rule is very straightforward. Whenever n is even, the first n minus 1 points, now n minus 1 is odd, I will use Simpson's rule, and the last 2 points I will use trapezoidal rule. I will illustrate it with a program. So, this is how I shall be using the Simpson's rule. Before I conclude this session, the execution will be in the next lecture, but before I conclude this, let us consider differential equation briefly. So, what are differential equations? In a differential equation, so this is the first order differential equation, y prime x, which is the derivative dy by dx, that is given by f x y. So, I want to solve this. So, how will I solve this? The strategy is again to expand y in a Taylor series. So, when I expand y as a Taylor series, so y at a new point n plus first point is given in terms of y at the xn plus h into y1 x1, h is the spacing between xn plus 1 and xn. So, y1 xn is the first derivative, h square by 2 factorial to y2 xn, this is my second derivative. So, I am expanding my function as a Taylor series which involves all the derivatives, and the error in truncating up to the nth term, I have taken up to the nth derivative, the error is given by Tn plus 1, this is the error in truncating the series up to n term, that error is given by h to the n plus 1 by n plus 1 factorial into y n plus first derivative at some point in between, at some point between xn and xn plus 1. This is my Taylor series expansion. So, yk, as I said, refers to the kth derivative. We will consider the two ways of solving this. One is by Euler method. What does the Euler method do? It approximates y at xn plus 1 equal to y xn plus h into y1. This is the first derivative. So, this first derivative is nothing but this function. So, it truncates here. That is my Euler's expansion. See this one now. The Euler's method, you expand the Taylor series only up to the first derivative, and you say at new point xn plus 1, I have y xn plus h into f xn yn. So, this is how I solve the differential equation. I know the derivative, f is my derivative. Using that derivative of xn yn, I generate y at xn plus 1. Now, to generate y at xn plus 2, I already know the y at xn plus 1, and now take the derivative at xn yn, xn plus 1 yn plus. I apply the same thing to the next step. What is my next step? Y at xn plus 2 is equal to y at xn plus 1 into h into f of xn plus 1 yn plus 1. Extend to n plus 2, n plus 3 and so on. I can do a number of steps. The only problem here, if h is very large, errors will accumulate severely, but if h is very small, then you can use this algorithm. So, errors are of the order of h square. So, this one Euler's method. There is one more very popular method which is called a Runge-Kutta method. I will briefly describe this, and these are not very hard to program. In the Runge-Kutta method, my y prime, which is the derivative, is given as a function of x and y. So, now I want to obtain an algorithm for the new y in terms of an old n. From yn, I want to determine yn plus 1. The formula is yn plus 1 is yn plus k1 plus 2k2 plus 2k3 plus k4 divided by 6. This is my Runge-Kutta algorithm. And what are these coefficients k1, k2, k3, k4? K1 is h into f xn yn. F already is known. So, k1 is h into f of xn yn. K2 is h into f of xn plus h by 2 plus yn plus k1 by 2. I already know k1. So, I evaluate k1 by 2. Then h3 is hf into xn plus h by 2 and yn plus k2 by 2. And finally, k4 is hf xn plus h yn plus k3. So, through this algorithm, I can solve yn plus in terms of yn, and once I get yn, I can go to yn plus 1, yn plus 2, yn plus 3. So, I can solve it for all the remaining values that I want, as many steps as I want. This is my Runge-Kutta method. So, I will conclude the lecture part here. Now, we will start our computational part of the work. If you remember the last time, there are three things I want to do. One is fitting a function through a given set of data points. Remember, we fitted a cubic polynomial through a set of data points. That is shown in my slide. This is shown here. You will see that I had y1, y2, y3, y4, okay, and I needed to determine these coefficients a0, a1, a2, a3. So, to determine these coefficients, these were all given in terms of xi's. Okay. So, I have 11 set of data points. For the 11th set of data points, first was the number of data points, then sum of xi, sum of xi square. These are all determined from our polynomial fit. This is a fitting a cubic polynomial to a set of 11 data points. Once we fitted those data points, this I need a0, a1, a2, a3. So, how do I get these things? I have to invert this matrix. So, if I invert this matrix and multiply on the right by the inverse, I get a0, a1, a2, a3. This is what was shown to be my set of coefficients, and my polynomial will be this is my a0, a1x, a2x square and a3x cubed. Actually, this was nothing but a function, sine hyperbolic function, and the data points were all for the sine hyperbolic function. Now, I shall show the program how to calculate this particular set of coefficients a0, a1, a2 and a3. So, I am in my directory here. So, let me do a PWD. PWD tells me the present working directory. You will see that the present working directory is, I will raise it further. Okay. So, my present working directory is home, BLTMB, prog, fitting. So, I want to go in that fitting function. I want to fit a polynomial through my data points. So, I shall see what are the files in that. These are all the files, okay, or let me just do ls. So, these are all my files in that fitting directory, fitpoly.f, fitpoly.f, fitpolyok.f, input1.dat. This is a matrix inversion and output. Okay. So, I will edit that fit poly and tell you what all that fit poly is doing. Okay. So, how do I do that? Vi. So, this is my program to fit a polynomial function. Okay. So, what I am going to do, we already considered a matrix inversion program. So, that matrix inversion program, what did it do? Once you have given a matrix, it will give you the inverse of that program. But here I need that matrix inversion as a subroutine to this program. So, this program will call that matrix inversion subprogram and multiply all the yi's by this inverse to get a0, a1, a2, a3. That is my purpose. So, let us go through this step by step. So, the first line here says implicit real star 8 a dash h o minus z. It means all the variables that I am going to use are in a double precision. Real star 8 means double precision, real star 4 means single precision. Whenever you invert a matrix, if all your operations are in double precision, you get much more accurate results. So, that is why I have this real star 8, and I have x data 11, y data 11. I had 11 values of x and 11 values of y. So, this is what is my data. Then I give a vector, my a vector a0, a1, a2, a3, 4 dimensions, and y vector also has 4 values. Okay. So, then I also define several matrices A 4, B 4, 4, C 4, 4. It is always good to define a large number of matrices which could be useful. Okay. So, what is the purpose? I have x data, y data, I want to fit the best polynomial through my y data. So, then my input is given in file 11. So, I say open unit equal to 11, file equal to input 1 dot dat, then open unit equal to 10, file equal to output dot dat. This is a parameter. So, sometimes you do not want to go on changing all the variables in the program. So, it is good to define parameters. Okay. So, here there is a slight problem. I have two open statements, one of them I should cancel. Okay. So, it is opening them twice. So, let me just so, I have commented, I do not want to open them twice. Okay. So, now I have defined an epsilon. Remember, in the matrix inversion program, you do not want to divide by a very small number. So, since 0 will rarely occur, anything less than that 0.0000, I think there are 1, 2, 3, 4, 5, 6, 7, and any number less than 10 minus 8, I take it as 0. Okay. So, I have done this. Now, read that n data and x data. Okay. So, first what I want to do is to read that n data. How many data points are there? I already know there are 11. So, from file 11 it will read n data. So, then once I read n data, it will read x data I, y data I going from 1 to n data. It will read the pairs for the n data number of points, and to make sure whatever is read is written, I write on the screen so that everything is visible. Okay. So, now I construct the coefficient matrix. Remember, I had a coefficient matrix which had sum of xi, sum of yi, sum of xi yi, sum of xi square, sum of xi square into yi, sum of xi cubed, all these sums I have. So, I am determining. So, in Linux, if you do anything wrong, it will create problems. So, I have to now delete all these things. So, I, in an attempt to show something, I use the mouse wrongly. Okay. 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 So, I initialized all these sums I have to calculate. Now, in this loop 150 I going from 1 to n data, I will generate all these sums. Okay. I will generate all these sums. Okay. So, for example, what is xi 5? Xi 5 is, okay, let us start from the beginning. Xi is equal to x data I, yi is y data I, xi 2 is xi into xi, xi 3 is into xi 2 into xi, that is xi cubed, xi 4th, xi 5th, xi to the 6th power. Then sum xi is sum xi into xi, sum yi is sum yi into yi, sum xi 2, this is the sum of xi square, sum xi 2 plus xi 2, do exactly sum xi 6 is sum xi 6 plus xi 6. So, this sums all the 6th powers of that xi. Okay. So, once you generate all the sums, I want to generate that matrix. So, my matrix I have called it A. So, A111 was 11, that is an data, A22 is sum xi2, that is A22 is the sum of xi square, A33 is the sum of xi to the 4th. This is all the matrix. Now, only thing I want you to see carefully, I have said I did not say A11 is equal to n data, I called it an data, because whenever I have a real variable, all real variables will start from A, B, C up to h. I, j, k, l, m, n are all integers. So, I want to start all real variables with those particular characters other than I to h. So, the other than I, j, k, l, m, n. So, these are all my, this is my matrix. So, once I have this matrix, now I have to generate that y vector also, because you know that y vector is on the right side, sum yi is the y vector 1, sum xi yi is y vector 2, sum xi square yi is y vector 3, sum xi 3 yi is y vector 4. So, now So, I will write whatever I read I want to write on the screen. So, that is what it will do, write. I have write that matrix A and write that vector on the screen, this is what I will do. So, now whenever I call that program to invert the matrix, it will change all the values of the matrix element. Therefore, the original value of A that I had, I am saving in an old array. A old array just saves me whatever is A, it is saved in the matrix A old. A old just saves the values of A. So, once I have done it, now I will call this subroutine, call Gauss E A B C N. So, this particular call statement, it calls the subroutine to invert the matrix by Gauss elimination. So, I have called it Gauss E. A was my original matrix, B was a blank matrix, B, C are not known, and N is the dimension. N is the dimension. Okay. So, it calls that matrix program to invert my matrix, and A will be an identity matrix and B will be the inverse. Remember, I use Gaussian elimination. There was matrix A and matrix B. At the end of the Gaussian elimination, what we got was A became an identity matrix and B is my inverse. So, that is how I will call this Gauss elimination. Then these are all some write statements. I want to write all the values of A, so that now A has become an identity matrix. I want to make sure it is an identity matrix. B has become the inverse. So, I want to write it. So, at this point I write A, I write B, I also write the determinant. Okay. I also write, all these are write statements. They are not so important, but they will help you to verify what you have done. So, at this point my x vector, okay, my x, so that final A naught, A1, A2, A3 I get by multiplying my y vector by this B. B is the inverse of A. So, when I multiply the y vector by inverse matrix, I will get all my xx. Xs is my A naught, A1, A2, A3. So, what I am doing through these loops, 590 loop, I am just multiplying a column vector y by inverse of that matrix. So, B is A inverse. So, A inverse into y is my x, x is the A matrix. Okay. So, that is my x. Then once I do that, I will write that xx on the screen. So, I want to know what are those A vector. A vector is what I am looking for. Once I have that A vector, that is my fitted polynomial. Okay. So, it determines through that. So, then what I want to do, after I get my coefficients, I want to compare my fitted polynomial with the original polynomial. Okay. So, this is that, come to this loop. What I want to do here, the rest is also interesting. I will discuss the rest later. What is important, once I determine all the coefficients, I want now to calculate the function and see whether it matches the sine hyperbolic function. Remember, I said that the actual function which was used here is a sine hyperbolic function. So, the 11 points that I have now fitted, I want to calculate in this manner. So, do 1100, I going from 1 to 11. My variable, okay, I want my variable is 0.1, 0.2, 0.3. My variable 2 is this variable is the value variable. I want to calculate my polynomial at that variable, okay, at 11 points in this case. Okay. Now, variable 2 is x square, variable 3 is x cubed. So, my polynomial which I want to calculate is A vector A naught plus A1 x plus A2 x square into A3 x cubed. This is the fitted polynomial. Okay. Poly is the fitted polynomial and analytic function is the actual function sine hyperbolic function. Okay. So, this poly is the calculated value using our program, analytic function is one calculated using the analytic function, and poly 1 is calculated using the coefficients which we got, these coefficients we got from some material in a textbook. So, I will calculate now 3 polynomials, one our fitted polynomial, one analytic function and one polynomial using the textbook polynomial, and write all that in file 12. Okay. So, this is the matrix. I will just comment on the matrix inversion program. Okay. So, this is a matrix Gauss-E matrix inversion program. Remember A, B, in the main program it was A, B, C, here I have called it A, B, A old n, and remember this n is a variable, this is the most important thing in my subroutine. So, what I have done, dimension A n comma n, B n comma n, A old n comma n. So, this means in the subroutine I have used a variable dimension, because in our case it was a 4 by 4 matrix. Suppose next time you want to do a 10 by 10 matrix, you do not want to create a new subroutine with a 10 by 10. So, this subroutine has a variable dimension, so that it can be called by any program of any dimension. So, this is a variable dimension in the subroutine, and this is the most important thing, and the rest of this is entirely your matrix inversion by elimination, that is exactly the same. Okay. So, what I will do now, I will execute this program and let us see what it does. Okay. So, I will now G Fortran so it has compiled without any problem. So, let us do ls, let us see what are all the files here. My input 1 data, let us just see vi. So, remember these are all my 11 data points, first point is 0 0, second point is 0.1 into 0.1002, last point is 1.0 and 1.1752. So, my input is intact. So, I will, so now I will execute, I have compiled. So, I will, so when I execute, okay, so it has executed. Okay. So, this is my original matrix which I which is my A matrix. Okay. Okay. So, I have written this original matrix here. Okay. So, this is my determinant, it is this is my inverse matrix, okay, inverse matrix, and matrix A after Gauss-E. See that A has to become identity matrix, B is my inverse, and what I do, I also calculate this is an important thing. I calculate the product of A and A inverse. The product should be identity matrix. So, look at this last value. Last value says product of the inverse and the original should be an identity matrix. You will see that all the diagonal values are 1, all the diagonal values are 1. Look at the lowermost part in the slide, all the diagonal values are 1, and off diagonal values are, let us say it is 0.40 into 10 minus 14. So, in a computer 10 minus 14 is as good as 0, and I get this because I have used that double precision. If I use a single precision, my 0 will not be 10 minus 14, but my 0 may be 10 minus 7. So, it also tells you what is the advantage of using double precision. So, I will just find the output file now, okay, that is output.dat vi. So, what we have done here, so this is the main result of today's work. On the left extreme slide, I have the variables. I took 11 values of the variable from 0 to 1, and first one was the polynomial calculated using the present program. The second one is my analytic function. The third one by a program by the result A0, A1, A2, A3 given in a textbook. So, you will see that this is my analytic function, the third one, this is my present program results, this is my other coefficients, and they seem to agree fairly well. Look at this, analytic function says 1.1752, this is an analytic function, and our fitted function gives 1.174, okay, whereas the other one gives 1.175. So, the starting value there is a problem, the sine hyperbolic of 0 is 0, but our 0 is actually minus 0.0007. So, the first point is not represented very well, the error is in the fourth digit. So, on a computer 0.0007, okay, 0.0007 is different from 0 by 0.007. So, that is my error. So, errors are in the 4 decimal places. Look at this also 0.6366, whereas from my program I get 0.6351, whereas I get 0.6365. So, there will be errors in the 3rd and 4th decimal places, okay. But still this is how we got a fitted function. In this case I knew that the function was an analytic function. When I do not know whether it is an analytic function, I can fit using my programs and then I can get a fitted function. What is the advantage of this fitted function? I can use a fitted function to really now integrate. Suppose I want to integrate the fitted function using a Simpson's rule. I can easily integrate using a Simpson's rule. I can calculate derivatives. I can do many things once I have a fitted function. So, what we have shown today is that given a set of points x and y, I can fit a polynomial through the points y through today we discuss a 3rd order polynomial. So, in the next class we will do random numbers and integration. The other 2 programs we will illustrate in the next class. So, what I urge you, you have seen this program, compile it and execute it so that you are comfortable in this program, and this program also tells you how to use a subroutine with variable dimension. So, I will conclude here. Thank you.